Today we're going to review some important things about acids and bases that you must know in order to move into acid-base equilibrium. First, let's talk about some properties of acids and bases. So we've seen the topic of acids and bases in grade 10 science, in grade 11 chemistry, and we should know a few properties of each of them. I would stop the video and see if you can come up with 2 to 3 properties and then check back in here for the list that I would expect you to know. So hopefully some of the properties that you listed were the taste of acids and bases. So acids tend to taste sour and bases tend to taste bitter if we are consuming them. And we don't consume anything in the lab, but certainly we come across acids and bases at home in the kitchen. And, most acids like vinegar, lemon juice certainly taste sour. Bases such as baking soda, green leafy vegetables, soap have a bitter taste to them. pH, okay, so the pH of acids is less than 7. And the pH of bases is greater than 7. Just a reminder that the pH scale runs from 0 to 14, with 7 being neutral. Both acids and bases conduct electricity. Okay, this is an important thing to know. They are both ionic. So even though a lot of acids have a covalent formula, the hydrogen and the anion that is present act as ionic substances. So both of these can conduct electricity. Depending on the type of acid and base that you have, some will conduct electricity better than others. So strong acids, strong bases conduct electricity very well because they break down 100%, but weak acids and weak bases only break down less than 50, which is where we'll be going with our equilibrium lessons. And so they'll conduct electricity, but not that well. Acids will react with metals and most metals. Again, you have to consult the activity series, and they'll form hydrogen gas. And bases don't. Okay, so bases do not react with metals. And so as a result, no hydrogen gas will get produced. And one other thing that we might want to mention about bases is the feel of them. So when you have a base on your skin, they feel slippery. Okay, so classic is, think of soap, think of shampoo. Okay, those are all bases. And then even if you had like sodium hydroxide on your skin, there'd be a slippery feel to it. So these are just some properties that we would expect you to know about acids and bases. In grade 11 chemistry, we learned the Arrhenius theory of acids and bases. And Svante Arrhenius was a chemist that was the first to define an acid or a base. And he said that an acid is a substance that dissociates in water. So you have to know that term dissociate is the same as ionize. Okay, this is exactly the same term. Just dissociate is like the better term, okay, that we tend to use. And when acids break down or dissociate or ionize in water, they form hydrogen ion. A base is a substance that dissociates in water to form hydroxide ion. So we have 2 examples there, excuse me, of acids and bases. And this is what his definition of each acid and base was. And he wasn't wrong. These are very good definitions. So for example, if we have HCl, when we place this in water, it's 100% dissociation. This is a strong acid. And so we get our 2 ions forming. We get hydrogen ion and we get chloride ion coming off. That hydrogen ion is the one that influences the pH of a solution. And then if we take sodium hydroxide, which is an ionic, so it tends to be solid initially, and we dissolve it in water, it will dissolve very well. Sodium hydroxide has very good solubility. And we release the 2 ions, and the AQ tells us that it's in solution. And this is the definition of acids and bases. It's a good one. However, there are limitations to the Arrhenius theory. So even though his definition is decent, there's a couple things we want to address. And one is the hydronium ion. So for example, when you have acids and that acids are breaking down to form a hydrogen ion, we know that this hydrogen ion is going to be present in water. And here's a water molecule with his 2 pairs of electrons. And we know that water is polar, okay? And what will happen right here, we get an extremely strong ion dipole attraction between the hydrogen ion and the negative end of the water molecule. And we form a hydrogen bond here like no other. Okay, so when we talked about hydrogen bonding in organic chemistry, like this, you can't even compare it because the hydrogen doesn't just have a partial positive charge, okay? It has a full-on positive charge. And so the hydrogen bonding that forms here is extremely strong, that this molecule acts as one ion, okay, still a charge because of that hydrogen ion, and we combine the H2O with that extra hydrogen, and we form what we call the hydronium ion, okay? So this is very, very important, and this is what tends to happen, is that we really form hydronium ion rather than just hydrogen ion. The other issue with Arrhenius is that there's all kinds of bases out there, namely organic bases, that don't have hydroxide in their formula. So Arrhenius said that a base dissociates and releases hydroxide ion. Well, consider ammonia, okay? That is a base. There's no hydroxide ion in there. Consider methanamine, okay? So CH3NH2. We know from organic chemistry that our amines and our amides are organic bases. Well, none of them have hydroxide in their formula. So, you know, Arrhenius didn't do too bad with his definitions, but a few limitations on them. And so we come up with a different definition. So Bronsted and Lowry were 2 chemists that said, well, you know, we better redefine acids and bases based on these limitations. And so they said that an acid is a substance from which a proton can be donated or removed, and that a base can accept a proton. And you may remember these definitions from last year. We tend to say that an acid is a proton donor and a base is a proton acceptor. Now, let's just comment on the term proton. So we would have addressed this last year, but remember that the hydrogen ion is called a proton in acid-base chemistry. And the reason for this is that this hydrogen ion has no electrons to his name, and he has no neutrons. So no. And as a result, he only has 1 proton in his atomic structure, and this is why we tend to call him the proton, only in acid-base chemistry. Now, in grade 11 chemistry, we also talked about conjugate acid-base pairs, and we had you simply identify them in grade 11. And we kind of warned you, you know, you'll need to know this for grade 12. Well, we will need to know this for grade 12. We're extremely interested in conjugate acid-base pairs. And these pairs differ in structure by only 1 hydrogen ion, right? So the proton of either an acid or also of a base. And what we do is we will look at these dissociation reactions or dissociation equations for different acids and bases. And you find a reactant that differs by 1 hydrogen with its counterpart on the product side. So I'm not stopping here at the hydronium ion because it doesn't even have a nitrogen, but I am going to keep going. And here is his pair, which is the nitrate ion, that does not have a hydrogen. So this is 1 acid-base pair. Then you look at water over here, and again, the hydronium ion, they differ by 1 hydrogen ion. So then we label them, and we look at nitric acid before, and we look at nitric acid after, and we say, what happened to nitric acid over here? Was he a proton donor, or was he a proton acceptor? What did he do? Did he get rid of a hydrogen, or did he accept a hydrogen on the product side? And we can see that he's a proton donor. So by definition, nitric acid is an acid. And by definition, we call the nitrate ion a conjugate base. Okay, so these conjugate acid-base pairs, 1 is acidic and 1 is basic. by differing by one hydrogen ion. We look at water and we look at hydronium and we say, okay, well, what did water do? Did water gain a hydrogen on the product side, or did he lose one? And we can see he gained one here. So by definition, he accepted a hydrogen or accepted a proton. Water is defined as a base. He's not basic, he's neutral, but water is really interesting. Water can sometimes act like an acid, act like a base because of its structure, right? He's made up of an acidic hydrogen and a basic hydroxide, so he can act as either or. And then the pair is what we call a conjugate acid. And it sure is, okay? This hydronium ion is very, very acidic, and that's, again, when we measure pH, we're measuring that. Let's look at the other two. So take a second, the other reaction. Take a second, draw lines connecting your two pairs, and then take a look at the hydrogen ions and determine, which is an acid, which is a base, and what are your conjugates. Stop the video, give it a try, come back for the answer. Okay, here are your two pairs. So we match up NH3 with NH4. And we look at NH3 before and we say, well, what did he do on the product side here? Was he a proton acceptor or a proton donor? He was a proton acceptor. So proton acceptors are bases, which means that the NH4 is what we call a conjugate acid. And it totally is. The ammonium ion has acidic properties. When you take the ammonium ion and you dissolve it in water, your pH goes down. Okay, it causes it to be more acidic. We look at water before and we look at the hydroxide ion after, and we say, what did water do with his hydrogen ion? Proton donor or proton acceptor? He's a proton donor. He lost it. So by definition, we call him an acid, and we call this hydroxide ion a conjugate base. This is how you label your conjugate acid-base pairs. You have to draw lines between the two, and then you label one as an acid or base, and the opposite one as a conjugate acid or base. It is really, really important to know and recognize strong versus weak acids and bases. When you are solving questions on acidity, for example, of acids or bases, the way you solve them is completely different if one is strong versus one being weak. So what we do is we teach you some rules as to how to determine strong acids and strong bases. And then anything else that doesn't fall into these categories is classed as a weak acid and a weak base. And we learned this last year, but just a reminder of what we're talking about. Strong acids and strong bases dissociate 100% in water, okay? And anything that's weak dissociates less than 50%. And that's when you get equilibrium and ice charts and all that stuff, good stuff happening. So let's talk about strong acids. How can we tell which ones are strong? So if you have a binary acid, so for example, hydrogen and some other element, these are the only three strong acids. They're the only three, okay? So HCl, HBr, HI, all strong. Anything else that's binary is weak. Oxyacids. So this is where we have, hydrogen with a polyatomic ion. So what we have to do is we look at the difference between the hydrogen and the oxygen in the formula. And when you subtract off the hydrogens and oxygens, if the value is 2 or greater, you have a strong acid. Okay, so right here, there's 4 minus 2 is 2, strong acid. 4 minus 1 is 3, strong acid. The only thing is that any organic acid, because sometimes with organic acids, right, we have like carboxylic acids, we have a lot of hydrogens and some oxygens. All of them are weak, okay? So be aware of that, and you should be able to recognize organic acid formulas and know that they are weak. Your strong bases, the only strong bases that you have are any oxides and hydroxides of the alkali metals, okay? Obviously except hydrogen. Hydrogen is not an alkali metal, even though he's in that group. And the alkaline earth metals except beryllium, right? It would not be chemistry without some sort of exception, like over here and over here. So any hydroxide or oxide, so sodium hydroxide, but also sodium oxide. magnesium hydroxide, but magnesium oxide. Those would all be classed as strong bases. Any other combination is weak. We also have learned how to calculate pH and POHs mathematically. So the pH of any acid is equal to the negative logarithm of the concentration of the hydronium ion. And for POH, the POH is equal to the negative log of the molar concentration of the hydroxide ion. Okay, so we have the two scales representing both acids and bases. Most people are commonly familiar with the pH scale, but we learned last year, like, of course, there'd be a POH scale that is measuring the amount of hydroxide ion that you have. Now, the opposite of these formulas, right? So instead of calculating pH, what if I know the pH and I want to calculate the concentration of hydronium ion? Well, the opposite of a logarithm is the 10 to the x button. So the thing is, we have to just be aware of some of these negatives. So if you were calculating the concentration of hydronium ion, you would take your pH value, make it negative, and then do 10 to that negative value. Same thing for hydroxide ion. So you would know your pH or POH value. You take 10 to the negative POH. And you can calculate amounts of hydronium and hydroxide for both acids and bases, because water is very interesting. Water breaks down a little bit. And in an acid, the water molecules that are always there will dissociate slightly and contribute some hydroxide ions. And in a base that is dissolved in water, some of those water molecules will dissociate a little bit and contribute some hydronium ions. So to go back and forth between the pH and the POH scale, this is a very important formula. You must know that adding those two values together will equal 14. And from there, you can kind of jump around between the two scales and do whatever calculations are asked of you. Let's do a few pH or POH calculations. So it says calculate the pH of a 0.045 molar solution of HCl. Well, we know that to calculate pH, I need to know the negative log of the concentration, molar concentration of the hydronium ion. And I just see that I have HCl. Well, we recognize that HCl is a strong acid, right? It's one of those binary acids. And it's going to break down and it's going to release hydrogen ion. But remember, hydrogen ion forms hydronium with water. And if this concentration is 0.045 molar, this is a 1-to-1 ratio of ions. Now, I know it doesn't look it, but you have to remember that there's that water molecule built in. And this is one thing you need to know. All acids and bases dissociate one hydrogen at a time. This is good news, because when we get into equilibrium, we'll always just have a 1-to-1 ratio, no 2x's or 3x's, anything like that. So as a result, we're just going to take the negative log of the concentration of hydronium, which is 0.045 molar. And everyone's calculator is a bit different. I know mine will give me the pH value that in a negative value, and then I neglect that negative, or I cancel it out with the negative over here in front of the log. So with pH values, we also tend to forego sig figs, and we always tend to write pH or POH values to 2 decimal places. Okay, so that's kind of a nice thing. The second one says calculate the concentration of hydroxide ion in a solution that has a pH of 5.87. Well, if you look at your formulas, if you're calculating the concentration of hydroxide, you need a POH value, and we've given you pH. So we need to calculate the POH of this solution, and that is not an issue. We're going to take 14 and we're going to subtract off the pH value. So we take 14 minus 5.87. So we get 8.13 as our POH value. And then we want to calculate the concentration of hydroxide ion. So that means that we have to take 10 to the negative POH. And when I punch that into my calculator, I get all kinds of leading zeros and I see just a 7 at the end of my display. You have to know that there's other values, other decimals beyond that 7. Make sure you know how to switch into scientific notation. And here we're going to round to sig figs, which is 3. And you should have a concentration of hydroxide of 7.41 times 10 to the negative 9 moles per liter. Now, you try this last one on your own, and then I'll give you the answer and make sure that you check that it works out. Any problems, let me know.